MOSFET complete design part called as testing and biasing part we have completed. So today I'm expecting we'll try to do these questions. Okay. Yesterday I already have given up the questions for you. These are the questions. These are the questions I think you have done it. These are the questions you have done it. So if you have any doubt in doing the problems, let us see. I'll also do it. Parallelly, you can check your answers where you have done the mistake. So one thing is good today. Whatever the questions we have in ECE, the same questions are in electrical. So no need of doing any new questions. Whatever the questions ECE wise, if I teach now, that are covered in electrical branch. So I'll take the ECE order now to teach the problems. Okay. Just one by one, each question we'll try to discuss, and we'll see the options for this. Each question, how the answer will be. The same questions are repeated in the chapter number 6 for electrical students. So that's why there is no need of doing extra work. ECE book if I cover, the electrical book is covered. Okay. After completion of this video, we'll try to present a new topic called as MOSFET current mirror techniques, and one more discussion we have is integrated inverter design techniques called CMOS inverter techniques. These two topics if we can cover. After that, we'll look about to practice remaining questions. With that, chapter 4 in ECE, chapter 6 in electrical will be covered today. So I'm expecting if the total class is being completing by 4 or 5 suppose. Today only we'll try to start a new module called as amplifier designs. So let us speed up the analog electronics. So I'll give some introduction basics for today class, so that tomorrow we'll have a long hours, because by 2 days I want to complete the amplifier designs. I don't want to go for 3 days. Within 2 days we'll cover the complete amplifiers. So let us take a good time tomorrow. Already we are taking 8 hours, maybe 7 to 8 hours we are taking. Let us take 1 hour extra or 1 and 4 extra daily. Around 9 hours we'll complete 2 modules. So that by 2nd of October we can finish the total BJT MOSFET analysis. So we are ready to start the options as the final session. Okay. So we'll do certain hard work tomorrow, day after tomorrow, taking some long hours. We'll finish the amplifier design part. Okay. So let us start these questions. ECE book, I'll do it. Let's see the questions. Question numbers. A very good morning to all of you. Very good morning. Shavik, Shalini, Piyush, Alam, Arpita. Very good morning to all of you. Let us start the class. Let us complete the workbook question step by step. I'm expecting some questions, at least you have done it with our fundamentals of yesterday class. Chapter number 4 we are doing now the questions. Chapter number 4. Okay. Before doing these questions, you know the concept. First I'll give the short notes for you. So whatever we studied, the basics, first we'll make a short notes for that. So what are the basics we have learned? What we have to remember in the classroom? Try to see the simple basics. I'll give the short notes for you. Then we'll start the class. You can see the short notes on. Short notes. The short notes based on your FET balancing and FET testing part. What are the main points we have to practice and recollect? Okay. You can just note on the short notes for 20 minutes. We can start the class. The first point is, if I consider JFET, what are the points we have to recollect when I see the JFET electronics? In JFET, we have one important equation we have been practiced yesterday. That is ID is equal to IDSS into 1 minus VGS divided by VP whole square. This is one important equation we have seen. ID is equal to IDSS into 1 minus VGS by VP whole square. This is called transfer characteristic equation of JFET. Okay. This point we should never forget in analog electronics to do the problems. ID is equal to IDSS into 1 minus VGS divided by VP whole square. IDSS, we know that IDSS, we call this as shorted gate drain current, we said. This is a shorted gate drain current. This is called shorted gate drain current. This is the current we'll get exactly when VG is equal to 0 volts. At 0 volts we'll have the maximum channel, so we'll get this current. And VP is called as pinch off voltage. Pinch off voltage. Pinch off voltage is a combination of two voltages. VGS plus VDS, I said. It's a combination of two voltages will become the pinch off value. And the pinch off formula, I said A square Q times ND by 2 epsilon. This is one formula for if it's an N channel. If it's an N channel. VP is equal to A square Q into NA by 2 epsilon, which is a P channel. One is for N channel and one is for P channel. We have the concept. One is for N channel, one is for P channel. Just 1 minute. For the interruption, sorry. So I think we have two formulas here, pinch off formulas. A square Q into ND by 2 epsilon. Another formula is A square Q NA by 2 epsilon. Where A is referring about half channel height. A is referring about half channel height. Of total channel, it is a half channel height we have taken. And ND is called as donor concentration. Donor concentration. Donor concentration is nothing for N-type doping concentration, we say. For N-type, the doping concentration we call it as ND. And NA we call it as acceptor concentration. Acceptor concentration. This is for P-type doping concentration. So these are the basic things you have to recollect when you are doing some analysis of analog electronics. Very simple things. And one more two important things you have to keep in mind. What is the next point is, you take this as one important formula, and this is considered to be a second formula, and this is considered to be a third formula. You can take 3 points like this. Fourth point is notation signs. VGS should be negative and VDS should be positive. These are the notations for N channel JFET. These are the notations for N channel JFET. VGS should be negative and VDS should be positive. These are the notations for N channel JFET. If it is a P channel JFET, point number 5, VGS will become positive and VDS will become negative. This is for P channel JFET. This is for P channel JFET. These are the basic things we have learned. Okay, P channel JFET. So these formulas we have to keep in mind for the concept when you are doing the problems in analog electronics. This completes the JFET basics. Let us one more formula you can add here. That is a GM formula we have created. GM is equal to -2 IDSS divided by VP into 1 minus VGS divided by VP. This is the formula of GM. GMO is called as maximum transconductance. Maximum transconductance is equal to minus 2 IDSS divided by VP. So these are the basic knowledge about JFET. JFET knowledge is like this. So 6 formulas if you can practice, you can work out analog electronics very easy in the JFET devices. So please complete this. MOSFET also will complete. MOSFET also will make it. Yesterday some student is asking, sir, is there any table form to have the practice? Yes. Today we'll make like a table form, MOSFET calculation, but equations, easy to practice and easy to remember when you make like a table form calculations. Let us make it as a beautiful table form for MOSFET techniques. With that we can start our today's journey on problems. So easily we can complete the problems. When you're doing problems, you have to feel happy because we have completed the content. The content how we are using in the problems will be the happiest point for us when you're practicing. Whether we are applying or not, that problems will explain us. Are we taking ETA as well? Ankumas, what is the meaning of ETA here? What is the meaning of ETA? What is your abbreviation for ETA? Please give a clear indication. What is ETA? Then I'll tell you as one or not. Okay, eta. We're talking about eta. Where is eta here? I think in this problem, I'm not saying any eta. Ankumas, where you are saying here eta? I can't understand. Eta is a word, comes in diodes and BJTs, not in the JFETs. In JFET we don't have any eta here. Okay? Eta means ideality factor. The ideality factor will come in diode chapter and in bipolar junction chapter, not in JFETs and MOSFET. Okay? Here there is no eta, my friend. So not done clearly. We'll just proceed for MOSFET now. Short notes on MOSFET. Short notes on MOSFET. It's clear, Ankumas, eta is not there in our class in JFET and MOSFET. Eta is a word comes in BJT classes, otherwise diode classes. Yeah, Akash, good morning. Akash Mishra. What is alarm? That. Okay. Panja, in pinch of voltage we have A square Q into NA by 2 epsilon we have. Okay. We don't have any eta here. Okay, Rahman, correct. I think this is not eta. This is not eta, my friend. I thought that this one. This is epsilon. Permittivity we call this as. I'll write here. Epsilon is nothing but permittivity, which is equals to epsilon naught into epsilon naught. This is known to everybody, I'm expecting. It's a permeability in A, permittivity. Okay? Right now, it is a permittivity. So permittivity here is epsilon naught into epsilon r. We have absolute permittivity and relative permittivity, two values. One is for free space, one is for your material. This will be given by the examiner, so no worries. This is not eta, it is permittivity we call. Okay? Permittivity. Yeah, Panja, I hope you understood. And one more Anupam Das. This is not eta, it's epsilon we call. We call this as epsilon. Permittivity or relative permittivity and absolute permittivity. This will be given by examiner, so no worries. Okay? So I'm expecting the next slide we'll see about MOSFET. We have one side you take what you can say NMOS. You take NMOS one side and make a table form like this. Second side you write it as a PMOS. One is NMOS, one is PMOS. In brackets you can write here the story is VGS is negative and VDS is positive. This is for depletion. This is for depletion type NMOS. This is the polarities. VGS becomes positive and VDS also becomes positive. This behavior is called enhancement concept. Enhancement type. So like this you can write the basics. And here also if you see VGS becomes positive and VDS becomes negative. We call this as a depletion type in PMOS. Depletion type. And VGS is negative and VDS also negative. We call it as enhancement type. These are very important sign techniques which will decide the type of MOSFET. Which will decide the type of MOSFET. Okay? Which will decide the type of MOSFET. So we have only 4 regions we write. First one, cut off if you want. The story I said yesterday class is, if you want to be cut off, your VGS should be less than threshold voltage. This is your concept. If you want to be cut off, your gate to source voltage should be less than threshold voltage in NMOS. Then automatically your ID will become 0. This is the story number 1. In the same story, if you are dealing here, if you want cut off in PMOS, nothing is there. Your VGS should be greater than VT, you have to check, such that your ID will become 0. The only thing is, when you study here, you do anti-opposite equation. When I say here less, you have to be there greater. That is the story you can learn. The second point is ohmic effect. If you go for ohmic effect, your VGS should be greater than or equal to VT. This is the first point for ohmic. Not only that, your VDS should be 0 volts or millivolts. A small voltages of VDS is considered to be ohmic effect. For this we have an equation. ID is equal to nu n Cox W by L VGS minus VT into VDS. So this is the knowledge about ohmic effect. Okay, I think it became a hobby for you. I'm expecting electrical students. It became a hobby for you. These equations: nu n Cox W by L VGS minus VT into VDS. Each parameter is an individual parameter. It will just comes in your mind like this. The same thing if I go for this ohmic effect here in PMOS. Here VGS should be less than or equal to VT. Previously it is greater than or equal you have to maintain. In PMOS it should be less than or equal to VT you have to maintain. And VDS should be 0 volts or minus millivolts, a small negative millivolts, because VDS is a equation style. Next, concept number 3 is triode region. Concept number 3 is triode. When you are going for a triode design technique, from ohmic to triode, your VGS, whatever you are seeing here, your VGS voltage should be greater than or equal to VT we have seen here, correct? VGS is greater than or equal to VT. But your VGS should be greater than or equal to VT has to satisfy, and VGS should be less than VGS minus VT you have to satisfy. It should be less than overdrive voltage. Then ID becomes nu n Cox W by L VGS minus VT into VDS minus half into VDS square. This is the complete approach. Okay. Same thing if I go for this one, triode effect. If you go for triode here, VGS is less than or equal to VT. It should be less. If it is greater, it should be less there. And your VDS should be less here, it should be greater here. The only style is, if you say greater, you make it less. If you say less here, you make it greater there. Opposite knowledge. So your ID will be nu P, nu n becomes here nu P, Cox W by L into VGS minus VT into VDS minus half into VDS square. So this is about your triode effect. Coming to the last one, fourth one, we have current saturation. Last one is current saturation. Here VGS should be greater than or equal to VT, and VDS should be greater than or equal to VGS minus VT. So previous one is less, it should be greater than what I put this, you will be in current saturation. Okay. So what is your equation here is ID is equal to ID is equal to half into nu n into Cox W by L into VGS minus VT whole square. This is your equation. This is your equation. And fourth one here, current saturation. Fourth one here is current saturation. If you want this condition should be opposite here, right? So VGS should be less than or equal to VT. VDS should be less than or equal to VGS minus VT. You can see that in PMOS techniques it should be less than, you will be in current saturation. Okay, greater than if you will be in triode in PMOS. If you are less than, you will be in current saturation because the graph will come in second quadrant. These graphs are coming in first quadrant, the graphs are coming in second quadrant. So what is the equation here is ID is equal to half times UP Cox W by L into VGS minus VT whole square. So this is the complete story about your current relations of NMOS and PMOS. Who is strong enough in these equations is the better person to do the problems in analog electronics. So why can't you practice like this after the class? Why can't you practice the session like this? It takes very less time to practice the MOSFET. Okay, MOSFET may not take much time. Hardly 4 equations, 4 regions. All are looking similar also. That is also the best point. The best point here is all equations are looking similar to each other. Only some sign techniques are different. So complete this and last short notes is about the biasing circuits. Take the biasing circuits, the equations we'll try to recollect, then we'll start our practice. Whole square. Yes, last whole square what was VDS. This is a whole square only here. This is a square. This total is square. Half into VDS square. Half into VDS square. Here also we have half into VDS square. This is square. Only we have square here, not here. Okay. Minus half into VDS square we have. Yes, Majinder. Maybe today class will go up to 6 or 6:30 today. Tomorrow class maybe I may take some extra time if possible. Today will be up to 6 or 6:30. No worries. The class will be up to 6 or 6:30. I will try to spend the time in the subject. Anyway, by October 2nd, the target is we have to complete the total amplifier analysis. With that, all devices will be completed nicely. We will have only one work with us called op-amp designs, one of the typical topics. So step by step, I have to teach each and every step. So I needed time for that. That's why we'll take a good time to complete that module. That is called op-amps. I think Majinder, you only told. I think op-amps is a very tough topic. Let's see when I teach the class. Let us understand op-amps how it will be. It will be tough or easy. We'll try to see in the coming classes. So please complete it. Last topic is biasing circuits. One time we'll recollect what biasings we have done yesterday and what is the backup equation for that. Just equations we'll remember. The short notes will help you a lot to study the total analog electronics very quickly. Correct? In every workbook when I'm teaching, there is a short notes for you. When you want to write a short notes, you can write a separate, take the notes after completion of my subject. You can take some 50 pages notes and you can write this whatever the points I said. You can write otherwise in the notes only you're copying it, that will be a short notes for you. In every part you can see your notes itself, the short notes. Okay, no need of writing extra notes if you're writing in the notes itself directly this content. Yeah, Sri Krishna, I think it's not 10 to 12 questions. In every exam, compulsory, op-amp questions are compulsory. That's why you have to learn like a good manner that subject. Okay? If you give me a good time, definitely I'll teach you in a beautiful manner, topic to topic. Each and every logic I'll teach you. You'll enjoy a lot my class. I promise I can do for you. You'll enjoy it, the subject. 100% guarantee you will be satisfied. Different copy for the notes. Okay. It's very good. Saha, it's good. If you can make a separate notes for short notes, separate notes for this content, it's good. Nice. No problem. According to your style, you do it. No problem. So let us see the final concept. That is your depletion MOSFET, biasings. One time we'll recollect. What are the biasings we have done? Depletion MOSFET biasing. Whenever you're doing, you have taken care that your gate to source voltage should be negative. This is the biasings we have done. The first biasing made like this is fixed bias has done this. Fixed bias has done this design like this. The fixed bias circuit looks like this. This is RT, this is VDD, this is VDD. I'm not taking RG into account. Straight forward I'm writing negative battery directly. This is your VGS and this is your ID. So this is called fixed bias circuit, which has used two batteries yesterday class. The first VGS, if you want, VGS Q in the problem, it will be equal to minus VGG. This is the first answer. If you want IDQ, it will come from your basic equation called transfer characteristic equation, K into VGS Q minus VT whole square, which is called as current saturation equation. Current saturation, we have to take the equation for balancing circuits because we are fixing the transistor in current saturation. So this is our story yesterday. This is our story. First concept is like this. Okay? This is the first story yesterday we have seen in the class. Not only that, if you see the load line graph also side by, this is ID, this is VGS. The graph we got like this. This is threshold voltage. You have been fixing the voltage as VGG minus VGG. So you got an operating point like this. This is your IDQ. So this is called graphical method. It's a fixed point, so the load line will be vertical to the y-axis. And coming to the next we have seen is cell bias concept. Cell bias circuit. The next circuit we have seen is cell bias. If 2nd October, if they give holiday, we'll go for 3rd. Okay? If they don't give, we'll try to work out the concepts. Because it's a live, maybe for live classes, I think they may not give holiday, I'm expecting. If holiday is there, we'll see, we'll invite. Let us see for tomorrow. The information will come for tomorrow. If holiday is not there, we'll finish the amplifiers. If holiday is there, we'll extend one more day. Okay? So this is about your fixed bias concept. Fixed bias is this one. Next I'm going for cell bias circuit. We have RS, RD. This is your VDD. This current is ID. This voltage is VGS. This is the circuit number 2. This is your circuit number 2. Okay? It's called cell biasing technique. Only we have cell bias, we don't have anything here. Okay? Cell bias circuit. In the cell bias circuit, main logic here is your VG is equal to minus ID into RS. So this is your equation called Ohm's law equation. Seeing the board you can tell VGS is equal to minus ID into RS. So this equation is very helpful to do the problems. VGS is equal to minus ID into RS. And what is IDQ here? If you want operating current, the formula is minus VGSQ divided by RS will give the operating current. If anybody give the information about VGSQ, we can find IDQ. If they give IDQ, we can find out the VGSQ in the problem. Okay? Kumar, why the screen is green here? Just refresh it one time. Refresh your screen. So log in again otherwise, if any problem comes like this. So how the graph you can show for this? The graph will be shown for this module is, it's a Ohm's law, maybe it comes like this somewhat. This is your graph. The slope of this line is 1 by RS with a negative slope. And the operating point we got like this. This is ID, this is VGS. So this is IDQ. And this is VGSQ we have. So this is the concept of Ohm's law method. Cell biasing load line analysis is like this. Only thing is this formula completes the cell bias circuit. And coming to the last one, we have is voltage divider bias. The last design is voltage divider bias. If the design comes like this, there will be RS, there will be RD, there is R1 and R2, like this. This is your VDD. This current is ID. This voltage is VGS. This voltage is VG. So seeing the circuit, if anybody asks me what is the relation we can write between VGS and ID here, means VGS we can write it as VG minus ID into RS. And what is the condition we applied is ID into RS should be greater than VG is required to make the VGS to work in reverse bias. This condition we have to apply. ID into RS we have to take more than the VG value. Yes, sir, Sumanta, VP and VT both are same. In your GFET classes, we call this as VP. Here we call it as threshold voltage. Both are same here. Both the pinch off voltage, both in MOSFET classes we call it as threshold voltage. Okay, don't get worried about that. Both will be same. No problem. In the exam, if they give pinch off, you take pinch off. If they give threshold, you take threshold voltage. Okay. So anyway, this is the story. Now what is IDQ formula here? Your IDQ formula will be VG minus VGSQ divided by RS. This is the way of studying the biasing circuits. Hardly takes 5 minutes to remember these techniques. Okay, biasing is not a big issue. 5 minutes mein aap aa jayega concept. Short notes will help you to understand within 5 minutes the story of biasing circuits. So we have only one graph is remaining. For voltage divider biasing, how the graph we have got yesterday is, this is your VGS, this is ID, and this is VGS. We have a graph like this, and we got some straight line like this. This is VG by RS, and this is your operating point, which gives here IDQ, and which is giving here VGSQ. The slope will be same 1 by RS. So this is the way how we study the package of depletion MOSFET. So depletion MOSFET have 3 biasing techniques. One is fixed bias, one is a fixed bias, one is a cell biasing technique, which is a Ohm's law, relation, and last technique is a straight line relation called voltage divider biasing technique. Hardly these 3 things will remember or understand it. I think doing the problems are nothing in analog electronics. In what book you'll see how I do the problems in an easy manner. So we have, enhancement mode is there finally. That also one time. We'll recollect the formulas. With that, you're ready to start the problems now. Problems may take 1 hour. 1 hour we have taken short notes. 1 hour we have taken problems. So within 2 hours we are finishing this job. So please complete up to here. Let us complete the remaining things. So boss, what is that 1.500 ohms? What is that answer, boss? You have given some answer to me. For which question? 1.500 ohms किधर से आया वो? From where it came? So first complete the short notes, then we'll discuss one by one the problems. Within 10 minutes we'll close the short notes. So remember the design part is very important. Okay, fixed bias you have to recollect. For self bias you have to understand the circuit how it is. And last one is voltage divided biasing. Daily you have to practice the circuits well so that you never forget the design parts. BJT biasing circuits how it will be, side by practice, and how the circuits will be for this FET biasing circuits. This will play a very key role in amplifier classes tomorrow. Okay, easily you will do the problems with the help of these biasing circuits. Okay, both good answer. Question number 1, 500 ohms is good answer. Nice, great. First question is okay, perfect. You have done it. Great. So let us complete the final issue. That is for enhancement MOSFET. Yes, we'll recollect the enhancement MOSFET. The last one we have is enhancement MOSFET. Enhancement MOSFET. Keep the heading. Enhancement MOSFET. The last one we have is enhancement MOSFET. In enhancement MOSFET, we have three designs. One is fixed bias. How you design means here VGS we have made it as positive. Enhancement means VGS we have to make it positive. For that I have taken my design like this. No RS, only we have RT, we have R1 and R2. Like this we have done it. This is ID. This is VGS. This is VG. This is called fixed biasing circuit in enhancement mode. Only thing is gate and gate to source will become same here. Your VGSQ will become directly equal to VG. And if you want IDQ, we can solve directly by Kn into VGSQ minus VT whole square. This is the way how we have solved. And if you want the graph for this is VGS, this is ID. If you want a graph for this is threshold voltage, this is your fixed voltage, that is VG. You got the operating point like this. This is called the first story. How I am finding IDQ with the help of fixed bias circuit. Okay? And coming to the next we have is voltage divided bias. Voltage divided bias. R1, R2, VDD, this is VG, this is VGS. Here same concept. Your ID becomes VG minus VGS Q divided by RS. This is my ID equation. So it's a straight line equation. VG minus VGS divided by RS will be the operating point here. It will be the operating point in voltage divided bias. So how the graph you can see for this? This is VGS, this is ID. We have a graph like this, the load line. One side is VG, one side is VG by RS. This is giving your operating point. So this is the technique we follow, voltage divided biasing technique. Sumanta, please remember one logic here. Voltage divided biasing, whatever we are seeing here, this is not voltage divided biasing, please remember. Voltage divided biasing will be fulfilled if there is RS in the class. Okay, that is called self bias also should be added to the voltage divided bias. Then only we can call it as voltage divided biasing. But here, only you have done voltage divider, but you have not made here RS, so that this voltage became same. When VGS becomes VG, it's called fixed biasing, we call it in electronics. Okay, you see divider, but it is a fixed bias circuit. You are fixing the voltage there. Voltage divider means RS should be included. That is the difference, these two circuits you have to understand. Okay, Samantha. So, I am coming to the drain to gate bias technique. Drain to gate bias. Drain to gate bias. So we have RD, RG, this is short we can take. This is VDD. This current is ID. So you can see the equation how you got is ID is equal to VDD minus VDS by RT we got. But VDS and VGS both are same in this concept. So IDQ became VDD minus of VGSQ divided by RT. The graph is coming same. This is VDD, this is VDD by RT. This is your Q point. So you can see all these issues in the class. I said that this biasing is easiest biasing, which have less number of components. Will be used for integrated biasings. These are used for small signal amplifiers where you will get a more swing. But here you will get a less swing, I said. In future class, we'll try to understand what is the meaning of a swing. In amplifiers, I'll teach you. It will have less swing, that's why it is not good for small signal amplifiers because we want more swing in the voltage amplifiers. Okay? That's why we use for integrated this idea. We use for small signal this idea. So this has been given the complete impact. What we studied yesterday, morning to evening. This is the short notes for you. If you complete this, we'll start doing the problems. 1 hour, we'll complete it. Just note on it. Within 2 minutes, I'll take some water and I'll come back. Okay? Take up to here. I'm expecting you're ready to start the problems. So I'm taking the order of EC book. You can just follow that questions. In electrical book, you can just note on the numbers of your questions. Seeing the problem, I think in electrical book, you can recognize it. You can write the numbers. Both are same nearly. Both are same nearly. So let us start doing the problems. Within 1 hour, I'll finish the problems now. Hardly 1 hour will take. Okay? Already both has given 2 good answers. Second answer is also correct, my friend. Great. -4 is the correct answer. Good. Other students, you can verify your answers. You can verify your answers. Okay? So let us start doing the practice. I'm doing for EC order. So chapter 4 it is in EC book. The first question itself, JFET question is asking. In the first question, he said that cell bias, he said, sometimes in the exams, they never give the circuit actually. You should have a talent. How to recollect the circuit is important. That's why you should have a good hobby to understand the circuit designs. Cell bias means in the mind you must get, okay, RS will be there, gate side nothing will be there, only RT, VDD will be there. That's called cell biasing technique. Whenever it's said like this, immediately you have to recollect like this. This is JFET and channel JFET. Maybe you will have some RS and we will have a short. This is your RT. So it's a depletion MOSFET or JFET, we have the same diagram. Both will have the same biasing technique. So what he said is, in the given problem, he's asking you, please can you calculate this RS? RS is asking by giving some data for you, saying that VGSQ is given in the problem. VGSQ is given in the problem is -5 volts. He has given. And IDSS he has given. And VP, they'll give compulsory these two values. IDSS is 40 milliamperes. Pinch of voltage is -10 volts. So what the trick here is, the formula for cell bias is VGSQ is equal to minus IDQ into RS. So VGSQ is known for us, but these two we don't know, IDQ and RS. Then what I'll do is, IDQ to find out, we have our main relation called transfer characteristic equation and take IDSS into 1 minus VGSQ divided by VP whole square. We'll apply this equation to solve IDQ first. It becomes 40 milliamperes into 1 minus VGSQ is -5, pinch of voltage is -10 whole square. Okay, this will become half. This will become half. So I think your IDQ answer will become 40 milliamperes into 1 by 4. Half square, 1 minus half is half square is 4. 1 by 4. That means answer is 10 milliamperes. So IDQ, nicely I found with your relation. 10 milliamps we got. Then automatically RS if you want, the formula is minus VGSQ divided by your IDQ will give you the answer. This is called cell bias technique how to solve. So it is a minus of -5 divided by 10 milliamperes. This will become 5 by 10 milliamps, which is not more than 500 ohms. So this is the way how easily I can solve with the basics. So the already Bose has given this answer 500 ohms. I think he has done the approach like this I'm expecting. He done like this concept. Who will understand the formulas and who will apply formula correctly, doing the questions of MOSFETs are very easy in electronics. Very easy. Okay? This will help you to get a confidence now about the problems. This is the way I'm getting my first answer. 500 ohms is the correct answer. So what about the second question? Second is also a simple question. You can see second question. He said the word here, P channel JFET. Please understand here, P channel he said. Whenever he said the word P channel, your VGS will be positive and VDS will be negative. This is the knowledge. If it's a P channel JFET, VGS will become positive and VDS will become negative. He has given actually the pinch of voltage he has given. He has given the pinch of voltage. VP is equal to 6 volts he has given and VGS also given, which is +2 is given. So these two information he has given. He is asking what is VDS value. So pinch off is 6, but input voltage is given, output voltage is not given. Then in the formulas I have given one trick for this. If you want to know the other value, we have a formula. Pinch off is the modulus of VGS plus modulus of VDS. First you can find out the modulus answer. At least you get the magnitude answer from this formula. So the answer is 6 is equal to 2 plus VDS. So VDS we are getting it as 4 volts. VDS we are getting it as 4 volts. But who will say this answer 4 volts? That will become wrong answer because it is just a formula of modulus we found. But really the sign will come from the notation. So VDS should be negative in case of P channel. Just you write the final stage. For P channel, VDS should not be positive. VDS should be negative. Magnitude wise you solve the answer and according to the JFET you write the sign. So answer there you 4 -4 also. But be careful. The answer should be -4 is the correct answer. Option B is the correct answer. So don't take 4. Take it as -4. ESC 2007 they have asked this question. So don't go for +4. Go for -4 because it's a P channel JFET. Okay. This is the way how good you get at the problems. Yeah, Bose, you're doing well. The questions, great. I think fourth question, the Bose has given the answer is 150 ohms. Great, yeah, nice. It is also self-bias question, correct? That's why we can do in the similar process. So I'm expecting, I think remaining students are not giving any answers, are feeling any tough. So remaining students also, you try to work out the problems and give the answers. Yeah, Piyush, Abhi, 150 ohms there, great. Before I'm doing, please try to solve it and give the reply so that I'll understand it, whether you're doing or not with me, parallel. You also do it parallel with me, fast and give the answers. Fourth question, 150 ohms are coming for the 2 students have given the answers. Let us see how it is coming for other students who has not understood. Let us see. Question number 4. He has given cell bias circuit again. We have RS. This is ground. And we have a battery of 10 volts. This is your IDS. This is your IDS. Okay? This is your IDS given in the problem. So by seeing this we can tell this is a cell bias circuit. This is VGS. This is IDS. So the formula is VGS is equal to minus IDS into RS. So in the problem what is asking is RS is asking again the question. Calculate. RS is asking. So if you want RS, you need VGS and IDS. I think in the problem, IDS is given 6.4 milliamps. He has given this answer directly, 6.4 milliamps. So VGS you can write as minus 6.4 milliamperes into RS. Only thing is VGS is unknown. So we're going to find with this formula, IDS is equal to IDSS into 1 minus VGS divided by VB whole square. With the help of this, you solve the VGS value. I think 6.4 milliamperes is equal to IDSS given in the problem is 10 milliamps. 10 milliamperes into 1 minus VGS divided by VB is minus 5 square whole square. So I think milliamps you can cancel. This 10 if it falls this side, it will become 0.64 is equal to 1 minus of minus plus VGS. You can take it as whole square. You get like this. Okay? This becomes 1 plus VGS by 5 whole square. So you can have a quadratic equation 1 square plus VGS by 5 whole square plus 2 into 1 into VGS by 5. So you just solve this equation, you will get VGS value in the problem. How much VGS is coming? Just solve it. So what is the VGS value? You just get this answer. How much you got? Please reply this answer. Yeah, everybody is telling 150 ohms, correct answer only. Can you reply this answer? VGS, how much you got in your problem? Yeah, Piyush, 1 volt, very good. By using quadratic method, VGS finally we have to confirm it as 1 volt because we have two answers we get. One answer positive, one answer negative. Okay? VGS, we got it as 1 volt. VGS is 1 or minus 1? 1 or minus 1 you got. Check that answer. If you thus, it's a 1, it's a minus 1 or plus 1? Because it's a, what we are doing, this concept is under depletion effects. So answer should be minus 1 should be the correct answer. VGS should be, we'll get this value as minus 1 volt. If VGS comes minus 1, then RS will be equal to VGS by ID with minus sign. So minus of minus 1 volt divided by ID is 6.4 milliamperes. ID is 6.4 milliamps. Therefore, is 1 by 6.4 milliamps. Okay? According to this, yeah, sorry. You can take square root directly here. 0.64 will be okay. Not like the square root like that. Yes, correct. Okay, Shah is telling take the square root. Directly you can make square root, easy problem. So answer is this value will be 1 by 6.4 milliamps. This total value, you can make a square root technique. 0.64, it will become 0.8 is equal to 1 plus VGS by 5. You will get like this. It will become minus VGS by 5 is equal to, if this answer comes this side, this will go there, it will be 0.2. So minus VGS will become 0.2 into 5 is 1 volt. So VGS will become minus 1 volt. Great. By using just the square root, it is better to write the answer. Correct. So it's coming to be close to 150 ohms. It's not coming exactly 150 ohms. In the problem also it said select the nearest value. 156 ohms we are getting, I think. That's why the nearest value we can take it as 150 ohms. Okay. The next question we have observed is 8th question is my next question. Correctly see that the 8th question is what type of biasing. Carefully see that one. 8th question. 8th question, if you see correctly. Question number 8. Question number 8. If you see clearly, this is also looking like cell pass. This is 1K. This is ground. This is your 10 volts. If you see the circuit, the source side, this is source, this is drain, this is gate. Source side, we have RS. Whenever RS is there, we can consider this as cell pass. Horizontally, they have written to confuse you. It's a cell pass circuit. And he has given an equation, ID is equal to 12 into 1 plus VGS by 4 whole square. So like this, he has given one equation for it. Transfer this equation. With the help of this, what data you can get in the class? With the help of this equation, what data means? IDSS we know in the equation, and pinch of voltage we know. Just will write the given data. In the given data, we have IDSS in the equation, which is 12 milliamperes, and pinch of voltage we can write it as minus 4 volts. Actually, this plus he has written here. It is 1 minus VGS by VB whole square. If it is minus, minus of minus, it will become plus. So pinch of voltage should be negative there, not positive. Okay? Pinch of voltage should be negative. You have to take. If these two answers if you take, the question he is asking is calculate the ID current. But problem here is both are unknown in the class. That's why I said previous class trick that quadratic method you can use. What is the quadratic method is? Minus VGS divided by 1 is equal to 12 into 1 plus VGS by 4 whole square. So we're going to use this yesterday class quadratic method because both answers are unknown. So I replace it as minus VGS by 1K. In place of 1K you write only 1. So finally we can write the current as milliamps, VGS value as volts. So this is your, otherwise you can write this as kilo ohms. Okay, but this is milliamperes. These 2 points you see. This kilo ohms and this milliamps will be cancelled actually. So answer becomes only minus VGS is equal to 12 into 1 plus VGS by 4 whole square plus 2 into VGS by 4. So like this you will get the quadratic method. If you simplify this answer, you will get 2 answers here. VGS Q will come as minus 2.26, one answer. If one is minus 7. Like this you are getting 2 results in the problem. If thus IDSS is not given, how can you say here AKI then? What is this? This is called IDSS. In the problem in the equation itself is given. This is called VB. Indirectly they have given the equation for it. IDSS they have given, pinch of voltage they have given. Rahman, now how I identified this is source, this is drain means wherever you will have supply voltage, VDD, wherever you have, that side is a drain. The remaining side will be source, like that I identified. Rahman, I hope here is minus 4 volts is pinch off. So you cannot go beyond this minus 4. So what is IDQ? Formula is Ohm's law minus VGSQ divided by RS. So answer will be minus 2.26 by 1 kilo ohm. So answer will be minus 2.26 milliamperes. So this is the way how I do the problems by quadratic methods. If the question comes like this is the way how to tackle the problem by using yesterday class quadratic mathematics. Okay, you'll get two roots values. In that you have to justify one answer. After getting that answer, you find out the operating current IDQ by the Ohm's law technique. It will be completed. Like this also they can ask you the questions. This is the best example for it. Question 9 will do it. Concept number 9. Question number 9. Question 9. It's a GATE 2014 question. Let us see how to tackle. Question number 9. Carefully see the problem. He has given a MOSFET, a resistance that is R with a VDD, and he connected a short like this. Yesterday already I taught you, whenever you connect like this, in testing problems I already taught you, this concept is called as current saturation biasing. It will be in current saturation automatically. The why? Because your VGS, gate to source voltage, and VDS both will be same. When VDS is equal to VGS, MOSFET is in current saturation, we can confirm it. So in everywhere you get this problem, so don't test it. It will be in current saturation. What he said is, the drain current ID, he has taken first drain current as 0.5. So first we will take ID1 current, which is your Kn into VGS1 minus VD whole square will take your VGS. Here VGS1, if you see, this is your VD. This was same. So what we can write is Kn into VD1 minus VD whole square you can write. This is your ID1 with respect to VD1. Second one, ID2 he has taken, which have the same Kn, MOSFET Kn is not changed, but VD2 has changed, minus VD whole square. Like this he has given two different parameters. The first case he has given one current with one voltage. This current, this voltage are different. Second case, this current you have to find, this voltage has changed. This is called ratio method technique. So if you take the ID2 by ID1, it will become Kn into VD2 minus VD whole square divided by Kn into VD1 minus VD whole square. So Kn will be cancelled because both have the same Kn. It's not mentioning about Kn means Kn are identical. So only thing is data ID2 will be equal to ID1 into VD2 minus VD whole square divided by VD1 minus VD whole square. You will substitute these values. ID1 is given as 0.5 milliamperes. VD2 is 2 volts he has given. Second one is VD2 is 2. 2 minus 0.8 whole square by VD1 he has given 1.6 minus 0.8 whole square. So this answer you have to calculate. This is a way called ratio problems. Just the first situation he has given ID1, VD1. Second case ID2 not given, VD2 given. Just have taken the ratio to get this answer. It is coming to be around 1.125 milliamperes. Very interesting questions. Your level will be like this in GATE exams. The level of asking questions will be like this. Just if you have the small basics that the system is in current saturation, the extra game you can play in the exams. Okay, the extra game will be done automatically by yourself. So this is about question number 9. Next target will be question number 12. Try to start doing this problem, question number 12. I'm thinking that question number 12 is also, it is in current saturation because it's a PMOS we have taken. NMOS or PMOS, who will connect a short like that between drain to gate, it will become current saturation. So I think this problem you can solve it. Question 12 you can solve it. Try to see what is the value of W and what is the value of R in front of the question. Yeah, 7 is asked if arrow is not given, suppose by chance. Okay, there will be one logic for you. In digital electronics, I think you have learned these techniques. If nobody has given in analog electronics or digital, it will be seen most of the times. Like this. Sometimes in your digital designs, you see like this without any arrow. But there's a trick here. This is considered to be NMOS. But if you want to show like a PMOS, they'll keep a bubble here. This will become PMOS. So no arrows will be there. Only in your digital IC designs, this is the way how analog circuits will be shown to you. If there is a knob, if there is a bubble here at the front, we call it as PMOS circuits. If there is no bubble, only you are shown normal, it is becoming an NMOS circuit. Okay, that is another way of representation. So don't get confused with this. Okay. So I'm expecting 12th question. Already students have given good answers. I'm very happy with your answers. Great. You're doing well. Question number 12. Perfectly you have done. Just myself, I'll try to verify my answers. Whether the answers given by you is correct or wrong, just I'll verify myself now. This is a PMOS with a 9 volts battery. There is a resistor to ground. And he connected here a short. This is called PMOS current saturation technique. Okay. So let us start doing this problem. So first what you have to do is, this says PMOS is in current saturation is confirmed. Current saturation. What is the only reason is VDS and VGS both are same. Gate to source voltage and drain to source voltage same. So now the point is, your ID formula we know, it is half into UP into Cox W by L into VGS minus VD whole square. We know that current saturation equation. In the problem I think current already given by him, 0.1 milliampere. He has given by himself 0.1 milliampere. Yeah, 0.1 milliampere. And Kp dash, yesterday I told you some notations for you. This total term only up to here, this we call it as Kp dash. Yesterday I given some indications for you. Kp dash or Kn dash is representing Un into Cox. We call it as process control parameter. Okay. Only this quantity is Kp dash. So is equal to half. You write half only. Kp dash is given 25 microampere per volt square. W by L. W is unknown, but L is given. L is 2 micrometers, yes given. L is given as 2 micrometers. So micro will be cancelled. Okay. And VGS will be how much? Your VGS minus VT whole square. VGS minus VT whole square. But in the problem, he has given VDS value. VDS given in the problem is minus 2.4. Whenever he has given this, that will become VGS value only. So it will be minus 2.4 minus threshold voltage he has given in the problem is minus 1.4. So keep it minus 1.4 whole square. So we got the complete data in the problem. Only W is unknown. Okay, W is unknown. Everything they have given in the problem. So if you solve this, you'll get the W value. So I think after calculation, I'm expecting the answer should be 16 micrometers you must get. Already most of the students have given the answer for it. 16 micrometers is a good answer for it. After getting this answer, I think finding this KVL at output will give you the R value. If you apply KVL at output, so if you go in this direction, this is your ID current suppose, I'm going in this direction, 9 is equal to, this is VDS, but I want VSD. So answer should be 2.4 you have to write, don't write minus 2.4, because it is VDS, we want VSD. So it is 2.4 plus ID into R will be the value. So R is equal to 9 minus 2.4 by ID. It is 9 minus 2.4 by ID is 0.1 milliampere. So R is equal to, you can find. How much you got? 66 kilo ohms. It is coming to be around 66 kilo ohms will be the answer. So this is a nice approach question, 12th question. 14th is the next question, question number 14. Question number 14 we'll see. Try to see how many students has done this 14th question because there is slight confusion in this problem. Most of the students may do mistake by seeing the problem. Try to see what is that mistake you try to do, just we will verify it. He's asking in 14th question, he's asking you what is the VDS voltage? It's a fill in the blank question. Yeah, 12th A is the answer. And Shavanidas is giving answer, good answer. 3 volts is perfect, great. 3 volts is the correct answer, perfect. You've done it nice. 3 volts will be the correct answer. It is also not a big question, just only small confusion is there. The confusion, what is that for the students see here? In question 14, the student will get confused with this technique is, this is arrow, he has given, below this is 5K, above it is 5 volts, and we have a short here. This is gate to source, he made short. So please remember this technique. When you are making the gate to source short circuit, I can't believe that it is in current saturation. Okay? Okay, no problem, Samresh, no problem. If any unit mistake, you try to correct it, no problem. It is not a diode connected MOSFET. It is not a diode connected MOSFET. If you want diode connected MOSFET, the gate and drain should be shorted. It is not gate to source should be shorted. This is different actually. If gate and drain is shorted, 100% correct, it is in saturation. But gate to source is shorted, I cannot believe that it is in current saturation. It can be triode also. So that's why this question we should not take directly it is in current saturation. If you take directly in current saturation, they'll design the circuit in triode, then it will be gone. That's why we have to do assumption only. Okay, we don't know. The short is different here. Actually, this is VGS set. VGS, he has taken here, 0 volts he has taken. So we'll just assume it. Assume your Q is in current saturation. We'll assume it. Don't confirm it. Because this is not a general short what we done till now. Short means you have to do here. This is the short, gate 2, but he done short here. So let us write the current equation. Half into nu n Cox W by L into VGS minus VT whole square. I have taken this relation to find out the current. I have seen the word, he said he has given some Kn in the problem. So yesterday class I told you, whenever they are not defining Kn as nu n Cox W by L or half into nu n, the default is this total value is Kn. In the exam if they don't tell anything, we have to consider this total as Kn in the problem. So Kn means this total value. So you can find out ID current. The total you can take it as 0.1 is Kn given in the problem. 0.1 milliampere per volt square into VGS 0 given in the problem. 0 minus threshold is negative minus 2 whole square. So answer is 0.1 milliampere per volt square into 2 square is 4 whole square. So answer is 0.4 milliamperes. Like this first I found out the ID because I don't know whether it is in current saturation or triode. Just I'll confirm it. So with this help I think we can find out VDS value. VDS is equal to 5 minus 5K into ID. You can find out by using KVL. VDS value you can find. So the answer is 5 minus 5K into 0.4 milliamperes. So answer is 5 minus 5K into milliamps becomes K kilo ohms, milliamps will be cancelled. 0.4 into 5 is 2 volts. So answer will be 3 volts we got. So VDS we are getting 3 volts, but don't confirm in the exams. First you verify it because it's only assumption I have done. Whether this answer is correct or wrong, just verify it. My assumption is correct or wrong, just it takes only 1 minute to test. So not testing I am doing, testing. What is the testing I have is VDS, if it is greater than or equal to VGS minus VT, then you will be in current saturation. So whatever the answer you got, just satisfy the voltage. 3 volts we got. VGS value is 0 volts minus, we got minus 2 volts. So 3 is coming greater than or equal to 2 volts. I think whatever assumption I have done, that is correct. Okay. Now I think your VDS is confirmed to be 3 volts. So this is the way how to do this question. Okay. Don't do it directly. They'll try to make you this question in triode region, then automatically your problem will be wrong. So they have a chance to make this as triode. So the short way to where I connect, why I call current saturation, please try to understand. This short is not a current saturation short. By chance it became a current saturation here, maybe in tomorrow it will become triode region. So I hope this is clear. Question 16 is the final task now. Question 16 and question 17, 2 questions are there. Let us see the next question. Question number 16. Question number 16. It's a voltage divided passing question. Gate 2017, yes ma'am. This is your voltage divided passing circuit. RS is 1 kilo ohm. Your RT is also 1 kilo ohm. And we have two resistors here. R1, which is 3 kilo ohms, 3 mega ohms, and R2, we have 5 mega ohms. And he has given here 8 volts. This is the biasing circuit. He has given some data for you, saying that your threshold voltage is 1 volt, and nu n Cox W by L is 1 milliampere per volt square. This is the data given, and he's asking you, can you solve ID? How much? Easily you can do it. These problems are not tough problems. Okay. Now the target is how to find ID. He's asking, but here VG is also not given, ID also not given. So we have to go for quadratic technique compulsory. Quadratic wise, we have to finish this problem. Yes, sir. That's correct. If drain and gate are shorted, you can say it is in current saturation. If if gate and source are shorted, you cannot believe it. It can be anything. It can be triode or it can be in current saturation. Okay. Just try to solve this problem. I'll take some water. So I think this question, 2 milliamps already some student has given the answer. Post great here. Great. 2 milliamps I think answer has to come. Let us see the procedure. What is the trick we can make is gate voltage here VGS voltage and we have here source voltage. This current is ID. Whenever you see voltage divided bias and threshold voltage is 1, we can say the first confirmation. As threshold is given positive, I can say that this is the enhancement MOSFET biasing. This is the enhancement MOSFET biasing. First confirmation. Because in the symbol we can't understand. Same symbol there. So as the threshold I have seen positive, I confirmed that it is an enhancement MOSFET biasing. First point. The next to ID relation we have is, your ID relation is VG minus VGS divided by RS. This is the knowledge we have. Seeing the board we can write. ID is nothing but VG minus VGS by RS. But in this question, he has not given VGS, he has not given ID. Then what you do is, apply this trick. ID is equal to Kn times VGS minus VT whole square. You take these two equations. This is one equation, this is a second equation. Keep this in VG minus VGS, keep 1 into. Your game will start with this equation. You just play a game on this. Find out the VGS Q value by quadratic method. How much is coming? Just find out with this technique. VG is already known. Here is a voltage division rule 8 into 5 mega ohms by 8 mega ohms minus VGS by RS is 1K is equal to Kn value. He has not given Kn, only this much he has given. So half is extra in Kn value in our class. In this I have represented Kn means half is also there and into 1 milliampere per volt square. Just I substituted this data. Half should be there. Extra term is nu n Cox W by L. That value he has given is 1 milliampere per volt square into VGS minus 1 whole square. So like this you do it and get me the value of VGS value. So one time if you get the VGS value, problem is solved there. Okay, the problem will be solved. I think you'll get here. You'll get here VGS. I think you must get as 3 volts. You must get VGS by quadratic method. If you solve, 3 volts will come. If VGS is 3 volts, then your ID is equal to VG minus VGS by RS, which is VG is 5 minus 3 by 1K. Answer is 2 milliamperes. You can see how nice we can do these problems. By quadratic method we can solve it. 2 marks questions generally they'll ask you when you're doing like a quadratic method. And they'll make you simple the quadratic equations. They'll not make you tough the calculations. Easily this answer will come like quadratic method equation. Okay. Very good. This answer is 2 milliamps will be the correct answer. What about the remaining questions? I think question number 17 is also a good question. Let us understand this question. Question number 17 will be the next question. Okay. Question number 17. Just read the question. Question number 17. Which is just looking like our previous EOS problems in BJT classes. Edge of saturation problems both input. Question number 16. Terminology is telling that it's edge problems in the class. So let us see that special question. Question number 17. This is your MOSFET. VDD. R is equal to 10 kilo ohms. This is your V0 and this is your VIN. This is the circuit we know. Okay. Given data is W by L he has given us 2. VDD has given 2. Nu n Cox he has given us 100 microamperes per volt square. And V threshold is 0.5. He is asking you transistor M1 switches from saturation to linear region. M1 switches from saturation to linear region. At that time, what is the input voltage? You can see the style of asking question is slightly different in this case. It's telling that it has to switch from saturation to linear, means you're asking me the question like this. This is your boundary. This is your current saturation. This is your linear region. You want to switch from current saturation to linear. Means if you want to go to here, you have to touch this boundary. So that means this concept comes under EOS design. So how much input voltage you have to create in the circuit such that you will just leave the current saturation. So whenever the type of technology comes, common sense, EOS feeling has to come. Therefore, EVOIS means in MOSFET class, it is VDS sat. Boundary level will be VGS minus VT. This is called EVOIS condition. Edge of saturation condition is this much. So if you write according to this, EVOIS equation, if you write, it is VDS becomes VGS minus VT. VGS is in the class, you can say, your VGS is input and VDS is output. You can write it as V0 is equal to VIN minus VT. You can prepare one relation like this. Your output will be equal to input minus threshold voltage. So then, we'll try to solve this ID current relation from this. First we'll solve the ID current relation. ID is equal to, in H we can write the current saturation equation, VGS minus VT whole square. This is called H problems. Whenever you are in the H, you can feel that you are in current saturation equation is satisfied. So ID is equal to Kn into VGS minus VT whole square you can take. So ID, I think in the problem ID is not given, but you can write like this. ID, this is your ID. You can write this as VDD minus V0 divided by R is equal to Kn into VGS becomes VIN minus VT whole square. This is the way you can write. But here, VIN, we are not interested because we want to find V0 in the problem. So what we'll do is, this above relation we'll substitute here called boundary relation called V0 plus VT in this equation. That's called boundary technique applied. So with this we can solve the V0 value how much? You can take a quadratic formula and solve it. Quadratic formula you can use. Maybe the answer will come for this is 1 volt we'll get for this problem. Quadratic. Then you can find out V0 is VIN minus VT. So VIN will be V0 plus VT. Okay. Then 1 plus 0.5. Answer will become 1.5 volts. These are very special questions. Okay. Answer is 1.5 volts will be the correct answer. 2 more questions. This type of questions they'll ask you. So whenever they say the word, you are switching from saturation to linear region. It is called boundary question. For boundary, you can take the help of this equation to solve the concept. First I found V0 by quadratic method. From that I found the input relation from that equation. So this is the story. T2 question I am not much interested to teach because T2 question every student will tell the answer because yesterday each and every example I thought you were testing problems. एक बार T2 को confirm कर दीजिए options में. T2 you can confirm yourself. Just tell you the answers only. You can do it yourself. That T2 question. And last one question is the T3 I'll solve it. T2 just try it yourself. PMOS problems they have given. T2 try to solve it one time. So T2 question, please try to tell me how much. T2 question. T2 question. He has given one MOSFET like this, 1.5 volts. This is M1. And second MOSFET he has given as 0.9. Like this he has given. This is source here, this is gate, this is drain, correct? First we have to find out VGS position. G is 0.5, S is 1.5. So 0.5 minus 1.5 will be equal to minus 1 volt. So what is the threshold voltage given in the problem is, your threshold voltage is 0.4 here given. So minus 1 is always less than threshold voltage, that is 0.4 we are getting. So that means your answer is coming less than 0.4. Whenever your answer is VGS is less than threshold, your MOSFET is on. M is on. M means here MOSFET. M is on is coming here. First point is confirmed. M is on. So what about VDS answer? 0 minus 1.5. Answer is minus 1.5 we are getting. So assume M in current saturation. Yes, I'll confirm that M is in current saturation relation. VDS should be less than VGS minus VT will be the current saturation relation in PMOS techniques. Less than is the answer. It is minus 1.5 is less than or equal to. VGS answer is minus 1 minus 0.4. So minus 1.5 is less than or equal to minus 1.4. Statement is correct. Minus 1.4 will be always greater than minus 1.5. So I can say that this transistor is in current saturation. So the first bit we can say it is in current saturation is confirmed. The first bit is M1 is in current saturation. If anybody done mistake, try to see. That's what I'm doing for you. It is in current saturation. Okay, by chance you may do mistakes because you are in learning stage. Confidence may not be there. That's why you do some mistakes. And coming to the second point, have you observed the trick? This is source, this is gate, this is drain. First you finish here, VGS value 0 minus 0.9 will be minus 0.9. So minus 0.9 is less than your threshold voltage 0.4. So I think M is on first confirmed. M is on. And second point I have seen VDS is coming exactly 0.9 minus 0.9. Answer is 0. It is 0 volts is nothing but M is ohmic. Whenever I said VDS is 0 volts are very small voltages, we call it as ohmic effect. So that means it's very clear to answer it. So one is in current saturation, one is in ohmic region we are getting. The last T3 question will be the final. Boss, your answer is correct, perfectly fine. Your answer is nice. You're doing well the questions. I'm very happy to see your answers. So T3 question, how to finish? The last question we are seeing, T3. We have a ground here. Current is 1 milliampere with minus 5 volts. This is 5 volts. Like this he has given the problem. And he said that half into nu n Cox W by L is 0.5 milliampere per volt square. and the threshold voltage is 1.2 volts. Lambda is 0. So this last letter, whatever you're seeing, lambda 0, and somewhere in BJT class we are saying VA, early voltage, that will be taught for you in the next lecture called after the break. I'm going to teach current mirror techniques in MOSFET. Compulsory. This content I have to teach for the class. Compulsory it is. That called as channel length modulation effect. एक बार बताना आपको क्या है, and one more is early effect. BJT class and MOSFET both I'll explain. There you will understand why these people will write like that. Why lambda 0, why early voltage infinite, क्यों बता रहे हो? That concept will be taught you in the next module called current mirror passing technique of MOSFETs. Here I'll explain you. Here lambda is 0 means don't worry, no effect. It's a theoretical problem. Practical means there will be some value. So you can leave lambda effect. Lambda is not there anything. He's asking you VDS is how much. Just you want to know what is VDS. Then how to catch this problem. So he has given here straightforward operating current 1 milliampere. That means this problem you can confirm that it is in current saturation because he has given directly operating current. So Q is in current saturation, you can confirm it because operating current he has fixed it there. Okay. If operating current is given directly, you can say that Q is in current saturation directly. So ID is equal to half into nu n Cox W by L VGS minus VT whole square. From this complete relation, we can solve only VGS value. ID already given in the problem. This becomes ID. So ID is 1 milliampere is equal to half into, sorry, this total content is 0.5 they have given already. This total is 0.5 milliampere per volt square into VGS is unknown. VGS minus 1.2 is threshold whole square. Just confirm the VGS value how much. So I think if you calculate this answer, VGS, you may get this answer as 2.614 volts. So you get some VGS value like this. Okay. So but we want here VGS value from here to here. You want the answer. So can you see that VGS is here? This is gate. This is source. So what is VS answer is? It is VG minus VGS. But gate voltage has been 0 in the problem. Gate voltage is 0. So minus VGS. So VS answer will become minus 2.614 volts. This is your source voltage I found with this trick. Then what is the VDS answer is? It is VD minus VS. Drain voltage is directly 5 given in the problem. Source voltage I got by VGS help. So you can write it as a 5 minus of minus 2.614 volts. So it will become 7.614 volts. Okay. So I'm expecting everybody getting that answer. Great to see your answers. So this is where how comfortably we can solve all the questions given in the competitive exams. So this level if you can reach, you're perfect for the competitive exams. Okay. So whenever you study the content, you do the workbook practice also parallelly so that your confidence level will increase. At the end when a test series question comes, you try to develop the questions. At this moment, don't read anything. You read content, you read workbook. Don't say number of questions extra. All these things don't do it because you're first learning the subject. When you're learning the subject, first take the help of the workbook to understand the questions, what the pattern of questions will be, and how the concept. Make the time for that. When it comes to December or November, at the time you can go for test series because you write some test series exams. At the time you see the questions. Is there any deviation? Is there any new question? If the question looks new, at the time you write something in your notes, extra important points for the content. Like that you study the problems. Okay? Unnecessarily don't waste your time reading different problems, all these things. What's the lambda is denoting here, sir? Lambda here is telling about channel length effect. Channel length modulation effect it is telling. Don't worry, after the break, this is my first topic in the current mirror topic. Extra basics I have to teach about this lecture because in the next amplifier classes, everywhere I use that word lambda and I use the word VA, early voltage. That story I'll teach you. Then I'll start the current mirror questions for you, designs. Because in MOSFET, current mirror is only 2 current mirrors. One is simple current mirror and one is Wilson current mirror. There are no number of mirrors are not there. But in BJT we have learned so many mirrors, but in MOSFET we have only 2 mirrors. It takes less time only to complete the task. So maybe up to here you complete it. Here I'm stopping it. We'll take a break. Now it is nearly 10:05. Okay. Around 11:30 we'll start the class. We'll take a break for 20 minutes. So by 11:30 shortly we'll start a new module today. That is called current mirrors. MOSFET current mirrors is the next lecture for you. Okay. That's my next class. Samresh, nothing is there. If you feel tough for the first time, revise the notes. Get the content first in your mind. Okay. Practice करके first mind में पूरा formulas, concept first understand करो. Then again start doing the workbook and you do it by yourself. If any mistakes are there, you have the video solution. You try to take it. So work hard. Then definitely anything will be easy. Okay. One time if you work hard and say that sir मेरे को तो tough लग रहा है, that is wrong. You just close your book. You read the content once again, formulas, all the short notes, and try to start doing attacking the problem. Where the problem is coming, notify it and understand it and do it once again. After that you will say that sir these questions are silly questions. The only thing is hard work is a matter. Nothing is there. Okay. Don't say the word tough any time in your life. If you revise it, definitely everything is easy in our life. Okay. We are not assuming Pada. Yeah, we are not assuming Q directly as a current saturation because he has been operating current directly. Whenever the person given direct operating point in the class, compulsory the transistors will work in current saturation only. No need of assumption also. If you have any doubt, you can just whatever the answer you got here, BDS, you can check it if you want. There is no problem. Definitely they will work in current saturation because of this operating current given directly in the question. Operating current. When they give directly operating current, then definitely the circuit will work in current saturation. Otherwise, if you have doubt, you can verify this answer with VGS minus VT. You can verify it also. It will be working in current saturation. Okay. Till then, we'll start the class around 11:30 again. New module I'm going to start 11:30. We're going to start the class, fresh topic. So it's called current mirrors in MOSFETs. Okay. Take a break for 20 minutes. We'll start the class. Okay. Previous slide is this one. Who want to take? Take. So I'm taking break for 20 minutes. 11:30 I'll start the class again. Okay.